Would you believe me if I said that everything, yes, everything we know about the universe can be found inside the smallest particle in nature? It sounds impossible, but it's not. I'm talking about atoms. Today, you're going to discover how these tiny structures hold all the forces that govern the cosmos. And as a bonus, you'll see how the universe literally exists inside you. But first, go ahead and subscribe to Yoru Curiosities and hit the bell, all right? Every week we share content that I promise will blow your mind. Let's dive in. So, what exactly are atoms? First, you need to understand that atoms are incredibly small, way smaller than you can imagine. To put it into perspective, a single human hair contains about 1 million carbon atoms. They're so tiny that not even the most powerful microscopes can see them. That's because they're smaller than the shortest wavelength of visible light. To actually see an atom, you need highly advanced technology, like a scanning tunneling microscope, which can detect the contours of particles. That's why atoms are considered invisible. Each atom is like a tiny arena where the fundamental laws of physics are at play, constantly. Inside them coexist the 4 fundamental forces of nature, the very forces that explain everything, from nuclear fusion in the heart of stars to the workings of your own body. These fundamental building blocks form everything around us. Me, you, the air we breathe, the stars in the sky, and even the most distant galaxies. And that's where our journey begins, looking at something invisible yet capable of explaining everything. The story of atoms starts long before modern science. Over 2,000 years ago in ancient Greece, philosophers like Leucippus and Democritus imagined that all matter could be divided into smaller and smaller pieces, until reaching a unit that could not be cut or divided any further. Hence the Greek word atomos, meaning indivisible. They believed these blocks came in different shapes and sizes, and that combined, they made up everything in the universe. This idea remained purely philosophical for centuries, only to be scientifically revisited in the early 19th century by the English chemist John Dalton. Dalton observed that substances always combined in fixed proportions and suggested this happened because each element was made of tiny, indivisible, identical particles, atoms. Dalton's model was simple. Everything is made of solid, indestructible spheres that join in different ways to create all we see. At the time, it was a huge leap, but far from revealing the atom's true complexity. Science, as always, needed more proof. By the end of that century, scientists were still trying to prove that atoms were indivisible, and one bold experiment would change everything. Physicist Joseph John Thomson, studying electric currents in vacuum tubes, noticed that a beam of particles was deflected by electric and magnetic fields. In short, this led to the discovery of the electron, a particle much smaller than the atom, carrying a negative charge. This was the first proof that atoms, contrary to previous belief, were not indivisible. They could indeed be split. Thomson pictured the atom as a plum pudding, a positively charged sphere with electrons stuck inside, like fruits in a dessert. It was a disruptive model, but soon to be challenged by one of his own students. Thomson's plum pudding model seemed convincing, until Ernest Rutherford, one of the greatest experimental physicists and ironically Thomson's former student, decided to test it. In 1909, Rutherford and his team conducted an experiment that looked simple at first glance. They took an ultra-thin sheet of gold, only a few atoms thick, and bombarded it with alpha particles. According to Thomson's model, the alpha particles should have passed through almost straight, since the positive charge was supposedly spread evenly. Most did, but something totally unexpected happened. Some particles deflected at large angles, and one in every 8,000 even bounced straight back, as if hitting something solid and dense. Rutherford was stunned. He compared the experiment to firing a cannonball at a piece of tissue paper and seeing it bounce back. The only explanation was radical. The positive charge and nearly all of an atom's mass were concentrated in a tiny, dense, positively charged nucleus. Orbiting it at vast distances were the electrons. This was a completely new model, breaking the plum pudding idea, but a major problem remained. Electrons are charged particles, and charged particles moving in circles should emit radiation. That means losing energy, right? If that happened, the electrons would crash into the nucleus in less than a millisecond. Rutherford's model explained the nucleus and electrons, but classical physics said the atom shouldn't be stable. How did atoms stay intact? The first attempt at an answer came from Niels Bohr. He suggested electrons move not randomly, but in specific orbits, with fixed energy levels. To jump or fall between orbits, an electron must gain or lose energy, releasing it as light. This explained stability, but not why only certain orbits were possible. In 1924, Louis de Broglie proposed a game-changing idea. What if the electron was not just a particle, but also a wave? Like a guitar string that vibrates only at certain frequencies, an electron wave fits only in orbits where it perfectly aligns. Orbits where the wave doesn't fit simply don't exist. That's why electrons don't collapse into the nucleus. The atom stays whole. This discovery also revealed that each chemical element has a unique set of electrons that emit light in specific colors, allowing scientists to identify the composition of stars and galaxies millions of light years away. Incredible, isn't it? Now, let's talk about the nucleus. Inside live particles called protons, all positively charged. Like charges repel, so theoretically the nucleus should fly apart instantly. But it doesn't. The strongest force in the universe, the strong force, holds it together. It acts at unimaginably tiny distances, stronger than anything else, easily overcoming proton repulsion. Without it, no atom and nothing in existence would stand. But protons aren't solid. Inside them live even smaller particles called quarks, held together by the strong force. This subatomic glue is so intense that trying to pull quarks apart only makes it pull back harder, like an unbreakable elastic. This accounts for almost all the mass of protons, and most of the matter in the universe. When this glue reaches its limit, it transforms energy into new particles called mesons, which travel between protons, keeping the nucleus intact, like messengers carrying the strong force. This same force powers stars and, when uncontrolled, can unleash a nuclear explosion. The strong force keeps the universe alive, yet could also destroy it completely. Even with the strong force at work, some atoms change naturally. This is called radioactivity. Another tiny force, the weak force, is at play too. It's 1,000,000 times weaker than the strong force and acts at distances smaller than 1% of a proton's size. Its action is mediated by heavy particles called W and Z bosons, over 80 times the mass of a proton. Through this, the weak force transforms one element into another, like carbon-14 turning into nitrogen-14, allowing us to date fossils and kickstart nuclear fusion in stars, creating the energy that keeps them shining for billions of years. Without it, no heavy elements, no life as we know it. Finally, the last force, gravity, the weakest of all, 1,000,000,000,000,000,000 times weaker than the weak force. It seems tiny, yet it builds the stage for the entire universe, forming stars from gas and dust, keeping planets in orbit, and holding our feet on the ground. Without it, no galaxies, no solar system, no you or me. All atoms feel gravity because they have mass, but almost 99% of that mass comes from the energy of the strong force holding quarks together. That's Einstein's famous equation, E equals mc squared, happening constantly. A falling apple, the tides, the moon orbiting Earth. All this happens because of what seems like a mere whisper among forces, a whisper that shapes the fate of everything in the universe. And all this unfolds inside a tiny atom. Surprising, right? When you breathe, trillions of atoms pass through your body. Some were created in stars that exploded long before Earth existed. This means the universe isn't just out there. It's here, now, inside you. So next time you look at the sky, remember, the entire quantum universe fits inside an atom, and inside all of us. You are the universe, and the universe is you. If you enjoyed this journey, leave a like, subscribe to the channel, and join us for more. If you made it all the way to the end, thank you for sticking with me on this journey through the universe. I can't wait to see you in the next video.